So what's the key concept of a vector? So a vector has a magnitude and a direction. Right? So magnitude means the size, right? The amount. And compared to the things that do not have direction, or we do not, the quantities for which we may not consider direction, those are called scalars. So they only have magnitude. So usually when we say magnitude, we are talking about positive quantities or zero. But sometimes we relax that and we allow magnitude to be negative. And then when taken into account with direction, it would just mean the opposite direction. If you say, for example, if I draw a vector, which is typically drawn as an arrow, and if you're representing it visually, the length of the arrow is supposed to be proportional to the magnitude, right? So if you're representing, for example, a distance in miles, you're not going to be able to draw miles long arrow, right? So there will be some mapping, like how you draw a map. There will be a scale. So, and you may not always draw it to a scale, but if you're drawing it to a scale, it is some proportion, like a centimeter, maybe X number of whatever, 10 miles, let's say. And then the direction is the direction of the vector. The one thing that is key to remember is that the same thing drawn here is the same vector. If I draw it with the same magnitude and direction, it's the same vector. Vector doesn't tell you where it is present. Right? There may be other information that tells you where, what is the position where we are considering that vector. But the vector itself doesn't tell you that. The vector just says this size in that direction. So for example, if you're if there is a two-dimensional space, let's say this is just ground, this is the north direction, and this is east, right? And something is moving like that in this field. So I could have, for example, here and here, I may have the same velocity. Velocity means speed with the direction. So I may be moving with this same speed in that direction when I'm here as well as here, right? So I could even take this vector anywhere, and that velocity is that velocity. I have to have some additional way to say, okay, it's present at this point. But otherwise, it's the same vector. I can move it parallelly without changing the direction and the magnitude, then it is the same vector. Another thing you'll notice is that typically the position where, or the point at which we are talking about the vector is usually placed at the tail of the arrow.
Okay.
But it's equally okay to draw the same vector this way. And that's okay too. So in a physics problem with forces, for example, right? The way I drew the first one may mean it's being pulled in that direction, if this is the object. Right? In another case, it could be it's being pushed from this place, like from behind, but in the same direction. If it is the same force, same magnitude, same direction, the effect will be identical on that object. And I'm considering a point mass model here. So you will see some of those things, but in general, you can take a vector and move it parallelly and it doesn't change anything. It's still the same vector. It will have a difference in certain situations. For example, in rotational motion. So if you have a door, right, this is a hinge. If you apply the same force here versus here, it will have a different effect. So the point where the vector is being applied will be critical there. And as you can see, this is not a point mass situation, right? There is an extent of the door, and we are talking about different points where you could apply the force, and the results will be. So I'm kind of highlighting where it will be important to be careful about the location of the vector. In other cases, if you're just talking about vectors in general, you can move them parallelly and not change its size, and it's okay. So how do we work with vectors? And at this moment, we'll just talk about adding and subtracting vectors. And later, we'll run into situations where we'll have to define the concepts of vector multiplication. So we'll take a look at the simple case of vector multiplication, which is scalar times vector. So this we'll look at right now. So if this is a vector v, it's written like that would mean it's a vector, right? In print, you may also see it made bold like that, right? And then they might not put a vector arrow on the top. And if I multiply this by 2, what does that mean? Same direction. So all it is modifying is the magnitude. So the result will be the magnitude is multiplied. If it is multiplied by negative, then the direction will flip. Okay, so if I multiplied it by, let's say, negative 1.5, so the magnitude is 1.5 times, but the direction is flipped. Okay, that is the scalar multiplication of a vector, addition of vectors. So let's say I have two vectors, this vector A, and I have some other vector B. Okay, so I want to find out what is A plus B. So remember, I can move these vectors around. I can pretty much bring this tail over here to the head of A, right? And then I can draw this vector parallel to the original vector and the same magnitude. Even though these vectors do not necessarily represent like positions and such, but when I'm trying to figure out what is their sum, as long as they're drawn to scale, it's like you started from here, you came here, and then you started from here, you came there. So it is called the resultant, the result of the sum. So this is A plus B. And if let's say, let me call it vector C, right? So it's still a vector. So if I start from the same spot, right, I could draw B first and then A, which is also the same sum. So this is, so that means vector addition is, what's the meaning of commutative? It comes from the word commute, like you go to work and come back, right? That's commute. So you go and come back. So here A is going to B's position and B is coming back to A's position. So they're switching position, but they're kind of going back and forth, right? That means the sum doesn't change even when A and B exchange places. So one thing you should remember in general that is true is that Subtraction is not really much different from addition. If, for example, if you say 5 minus 7, right? This is same as 5 plus negative 7. So subtraction is the same as addition of the negative, which is in general terms is called the additive inverse. Additive inverse is something, if you add it to something, then that becomes 0. Since 7 plus negative 7 equals 0, these two are additive inverses of each other, which we loosely we call it negative of one number. So negative of negative 7 is positive 7. Negative of positive 7 is negative 7. So similarly, the vectors work the same way. If we say A minus B should be the same as A plus negative B, then I should be able to apply this same rule as addition and figure out, because we already know what negative B is. So I can draw negative B here, right? And I can add A and negative B. This is negative B. So A plus negative B should be that.
Okay.
And if I call this as vector D, then that is D. And you can do normal algebra here. For example, if I say A minus B is D, then I should be able to get A equals B plus D. D plus B, B plus D is commutative. So I should be able to do B, so this is B, B plus D, which you can see here, this is D, right? B plus D is A. But what we will typically be working with, we'll draw these pictures to understand and represent what's going on. But what we will actually be using for doing the computations is analytic geometry. When we do geometry, for example, I draw a triangle and I have the dimensions and I find its area, things like that. I don't deal with its coordinates, right? If I know this is the base and this is the height, and then I say area is half base times height, I'm not really converting it to any coordinates. But we also know how to put that in the coordinate plane, the Cartesian coordinates. And then I can start using Pythagorean theorem and distance formula and equation of lines and things like that. And I can just do algebra with the coordinates. For example, there's a way where you can compute the area of a triangle using the coordinates. So you could find this distance and that age, or there are other ways that we'll learn later that you can actually directly find the area of the triangle if you knew its coordinates. So when we work with coordinates in a coordinate plane, we translate the problem, the geometrical problem, into the coordinates, and then it becomes an algebra problem. Then we do the algebra and find the answer. When we do it that way, then it is called the analytic geometry. So there was a mathematician named Descartes who popularized and kind of, he may be considered one of the inventors of this method, but he is the one who kind of popularized this. There was another mathematician at the same time, I think Fermat, some others were doing it, but this Cartesian is coming from his name. So these are the axes, right? Normally we call this the x-axis and the y-axis. These can also be referred to as dimensions. And these are the orthogonal. Orthogonal means perpendicular. Perpendicular directions that we want to use for our coordinate system, right? Because if I say 2, for example, right? and 3. So this point is 2, 3, but it won't mean anything unless I show you the axes, where the origin is and where the axes are, right? Because if I have a coordinate system like that, then 2 and 3 would work like this, right? Also in physics, this is called frame of reference. So you place an origin somewhere and you place the direction, the axis along some, and then you can talk about the coordinates. This is vector V, let's say. What we do is we identify the components of the vector along the x direction and the y direction. So I can think of this vector as a result of adding two vectors. One is along the x-axis, the other is along the y-axis. So I can say, okay, this is my v sub x vector, and then another v sub y vector. V sub x component plus v sub y component equals the, and their magnitudes are just written like that. Okay, so you may see it written as or written like this. So usually if you just drop the arrow on the top, that means you're talking about its magnitude. How are these three related? These three, Vx, Vy, and V. What you can use the Pythagorean theorem or the distance formula, same thing, right? So that's how you can find the magnitude of a vector. If another way to tell directions, which you might have seen in, for example, polar coordinates in calculus, right? That's another common way to do it. So this is the V that makes angle theta with the x-axis. So now how can I figure out the components? Vx and Vy. Vx is V cosine theta and Vy is V sine theta. Why would we care about components? So let me talk about that. Let's take a simple case. Suppose if I have two vectors along the same direction. Let's say the magnitude of A is 3 and the magnitude of B is 2. What do you think the result C is? So C is 5 along the same direction. So when two vectors have the same direction, you can simply add their magnitudes and that's the magnitude of the result and the direction doesn't change. So let's see how that can simplify addition of vectors. Okay, suppose I'm adding those two vectors. Now they don't have the same direction, right? What are the components for this one? Now if you look at the resultant, what do you notice? So this magnitude is pretty simple, AX plus BX. It means if I'm working with the components, my life becomes very easy. I can just add the stuff. One thing you have to remember that is if the arrow is pointing backwards, you should account for a negative there. We could add the magnitudes if they were pointing in the same direction, right?
Mhm.
So we have to assume, okay, my direction is X. For the X component, my direction is X. If I'm going in the negative X, I have to move the negative into the magnitude. I have to add A and B to find C. I can take the components of A and components of B, add the corresponding components that will give me the components of C, and then I can put them together to find the vector C. Okay, so that's the general approach that gives us, it allows us to use the components along the axis and go back and forth between them depending on what I'm trying to do. If you're taking the angle, if you're taking this angle as theta, going counterclockwise, opposite of the motion of the clock hand. From the x-axis, then the cosine theta and sine theta, they'll all give you normal appropriate signs, right? If you went like into the second quadrant, the x component will become negative. So all of that will play out. But sometimes what happens is you may be given, or you may draw, depending on the problem, you may draw this angle as, let's say, alpha. Okay, so this coordinate is negative, and this will also be negative, correct? So now if I'm trying to find alpha, I have to be careful because I'm already assuming it's in this here. And if alpha is 30 degrees, it means 30 degrees to the left of the negative y-axis.
Mhm.
So if you draw it like this, then you have to be working with things very carefully. Suppose you do the calculations and alpha comes out negative. What does that mean? If alpha is negative, that means you are here. How will you find out the angle? This is, let's say, 7, and this is 9. Then how do I find theta? If you were trying to find alpha here like that, then you would be taking these as positive quantities.